behavior, especially probably we are going to hear about more about this tungsten ditelluride work, which is probably one of the hottest materials in the recent years. So here we go, David.
Hello. Thank you. Thank you very much for the introduction, Philip. It's great to be here. It's an honor and a pleasure. I've never spoken at Harvard before, and it's been something of my dreams for a long time. Yeah. So let's get started, and if I remember other things I should have said at the beginning, I'll say them later. I'm going to be telling you about tungsten ditelluride. The work was done with, obviously, quite a few people are involved. Some key members, key collaborators. The most important of all is my colleague Xiaodong Xu from the University of Washington. I'll also show you work that was done in collaboration with Josh Falk at UBC, Yongtao Cui at Riverside, and of the grad students and postdocs who participated, the key players were Ziyao Fei, who is still with us now as a postdoc. He was my grad student. Tao Nu is a postdoc. And Sanfeng Wu, who's now a postdoc, who's now a papelado with Pablo Guerrero Herrero, and our most ferocious competitor. But until a year ago, he was one of us. So that's the way it goes. So let's get started. No grand introductions here. I'm just going to tell you about the material tungsten ditelluride and tell you about these properties we've been studying. But here's a summary of some of the facets of this material. It's a semi-metal. It has this orthorhombic structure, so it's layered. Okay, it has this rectangular unit cell in the bulk. So its crystal habit, as a picture of a crystal, it basically looks like little planks, little rods. It grows that way. And it exfoliates pretty easily. So we can, easier than a lot of things, but not trivially. Okay, and looking in a little bit more detail at the structure, it has these tungsten planes that are surrounded by tellurium on both sides, and each tungsten atom is in the center of this distorted octahedron of telluriums. And it's a fairly distorted low symmetry structure. The space group is PMN21, which is non-symmorphic. I'm not sure whether that really matters, but maybe it does for topological properties. But if you stare at this stuff, you realize that there are basically kind of tungsten chains going along in one direction, along one axis, the A-axis. And a set of bonds along a chain are highlighted in red there. Okay, so there are chains within the planes. It's anisotropic within the planes. And there are two non-equivalent telluriums, if that's important, although all the tungstens are equivalent to each other. It has very large spin-orbit coupling, because both tungsten and tellurium are heavy. And it's a semi-metal with small electron and hole pockets. Here's a band structure calculated by Hassan et al. A year ago of the bulk. So these are the bands in this three-dimensional Brillouin zone. And there's holes here near gamma in a fairly wiggly valence band edge, and that's overlapping with a little bit of the valence of the conduction band there, which is just off from gamma. And and there's nothing else at the Fermi surface. Just a little bit away above the Fermi surface, there's possibly a Weil point, type 2 Weil point. So this was the material that Bernavig et al. Proposed would have type 2 Weil points in it a couple of years ago. It's still controversial whether these Weil points are actually there, although they're thought to be there in similar materials, molybdenum ditelluride in particular. But that's why one reason we can justify calling this a topological semi-metal in the bulk. Okay? It also had this very large magnetoresistance. So as you cool, the resistance drops, but then as you apply a magnetic field, the resistance comes back big time, and you get a huge, extreme magnetoresistance at low temperatures, and that earned Ong's group a Nature paper a couple of years ago, and that's kind of relaunched the career of tungsten ditelluride. That's the first time I heard about it, was when it was in this paper here. It has several different career paths. It's being used by Ralph's group as basically a low symmetry, strong spin orbit coupled medium for their spin torque manipulation games. And I believe there are also people here at Harvard employing it because it fits strong spin orbit interactions. And one thing I should mention here, and I'm going to emphasize it towards the end of the talk, this is actually a polar material. This is a polar space group. And if you're not sure what that is, I'll come back to that later. Now, our interest is in taking things like this down to the monolayer limit. And our original motivation for working on this material was it was the only semi-metal we could get our hands on. And we were interested in looking at two-dimensional semi-metals. Graphene's been done to death. Lots and lots of two-dimensional semiconductors are now being studied. But what happens in between? What happens to semi-metals when you take them down to this 2D limit? Massive semi-metals. There's been remarkably little work on this, I think, and there's a good reason for it too, which is that almost all of these materials are not very stable. Their surfaces oxidize. You want to play games down in this limit, you have to deal with their chemical instability. And so all the progress is being made recently on this material and others by working with them in a very carefully controlled environment, right? Preparing these monolayer devices in a glove box. And that's what is basically allowing us to do these experiments. It's the key thing. So you take this thing down to the monolayer, and it was predicted by these guys at MIT 3 years ago that it was calculated that the band structure of this is essentially topologically non-trivial. If you calculate the Liang-Fu Z2 invariant, and you pretend that there's no overlap of the valence and conduction bands, you treat it as a semiconductor, you get it being in the non-trivial class. You expect it to be a two-dimensional topological insulator. The problem with that is that their band calculations imply that it should not be an insulator. It should be a semi-metal. And the valence and conduction bands would overlap. Nevertheless, if they calculate the modes in a finite strip of this material, they get helical edge modes, which are what you expect from a topological insulator. Spin polarized edge modes propagating in opposite directions along the edge. This is K along the edge, essentially, here. And these are the spin up and spin down modes, which cross at time reversal invariant points. And you get these edge modes, but they should be degenerate, according to their calculations, with the bulk. So these fuzzy blue regions here are the bulk conduction and valence bands overlapping with these things. So it's not an insulator. It's topological, but it's not an insulator, according to their calculations. ARPES measurements on potassium-doped material done by Shen's group in collaboration with Cromie show this is a ARPES measurement zoomed in on the gamma point here. And you indeed see this hole, this valence band at gamma, and then these two electron pockets just on either side of it, which you can see here in the Brillouin zone, which I forgot to point to earlier. Okay, and then you can argue about whether there's actually a gap here, or whether a direct gap, or whether these things overlap. Sorry, an indirect gap. These guys claim that there's a 55 millivolt gap there, in spite of the calculations implying otherwise. Some STM measurements that came out last year indicated that a gap forms as you cool the material. So, during the last 2 or 3 years, we figured out how to make monolayer devices out of this stuff, okay, just basically by working in a glove box and encapsulating them with boron nitride so they don't oxidize. And we found that they indeed have edge conduction, which shows in every way seems to be consistent with these helical modes that you expect from the quantum spin Hall effect on a 2D topological insulator. And we submitted our paper on that first in September 2016. It came out in last June. And then Sam Fung was one of our team at that point. But Sam Fung Wu then moved to work with Pablo and a grad student at MIT, and as I said, became our fiercest competitors. And he's also just had a paper out in Science this month where they see similar behavior to us, but with a slight refinement, which I'll get to in a minute. So we're not the only people who have seen this, and we see what we think are helical edge modes on this monolayer material. And we also see that the bulk is insulating, in spite of these predictions that it would be metallic from band structure calculations. But I'm going to claim that it's not a trivial insulating state. It's not a single particle insulator. All you need to know about our devices, shown in this schematic. As a cross-section of a device, we have this monolayer, this exfoliated monolayer or bilayer or trilayer that's sandwiched between HPN on top and bottom as a dielectric, and then with metallic graphite above and below that. And normally we have thin platinum contacts sandwiched in with that. Okay. And we have different contact patterns, and sometimes we have more complicated stuff above and below, but this is essentially what we have most of the time. So you can just think of that as this 2D sheet of WTe2 stuff with metallic planes with bias voltages on either side. And we expect that just by juggling these voltages on top and bottom, we should be able to change the net charge density on this sheet. We can dope it with say, by putting positive voltage on both of those, electron dope it. Or we can apply a transverse field. So we can put opposite sign voltages on the two sides of the gate voltage and put a displacement field that goes through this material. Yeah?
Contacts are n-doped, p-doped? Like what should be the effect of the...
That's a good question. Yeah. The nature of the contacts is a really good question. It's very hard. I don't have much to say about it. So we do get electrical, we do get ohmic contact to the bulk, but it's a contact between platinum metal, or sometimes graphene, and this two-dimensional sheet, and we get reasonable contacts to the edges as well, but I can't tell you, specifically whether it's. I mean, one complication is that this material, as far as we understand it, is strongly correlated. It's not a semiconductor, right? So we can't really say it's got electron-type carriers or hole-type carriers in it, and we can't talk about a Schottky barrier at the contact. Okay. Right, I'm going to tell you about the many faces of this surprising material that we observe in these such monolayer devices. And the first of these faces is the one that I've alluded. My forward and backward buttons don't work properly on this. Is the one I've alluded to so far. This prediction that it would have helical edge states and it would be a topological insulator if it were gapped in the bulk. So here we have, to start with, measurements, two terminal measurements between two adjacent contacts on a sheet of trilayer WTe2 and a bilayer and a monolayer. And here we're just sweeping the common gate voltage on both top and bottom gates, so we're changing the doping density in this material. In the trilayer, it's basically almost gate independent, and moreover, as you cool it, the conductance goes up. So it's really metallic. At all gate voltages, it's just metallic. In the bilayer and the monolayer, you see something different. You see that at high doping levels, in both the bilayer and the monolayer, it's metallic again. The conductance goes up as you cool it. But in a range of low dopings, the conductance drops as you cool. And there's a characteristic temperature, which in the monolayer case is about 100 Kelvin, and the bilayer it's about 20 Kelvin. There's one difference between the bilayer and the monolayer. If you look closely, you see that in the monolayer at the low temperature end, the conductance doesn't go to zero, but it goes to a finite value. There's a plateau of conductance, almost independent of density, over a range of densities. And in the bilayer, it actually falls to 0 at low temperatures. Now, I'm not going to go into the full story of how we justify this because I don't have time. Unfortunately, I'll just show you a few illustrations of this. But I'm going to state that we are quite sure that this plateau of conductance here is coming from pure edge conduction. In this region here, all the current is flowing very close to the edges of the device, just as you expect in a two-dimensional topological insulator. Those are the boundary modes. In the bilayer, there's no edge conduction. So a similar process happens where the conductivity decays when you're close to 0 doping as you cool, but in the monolayer, you're left with conducting edges, and in the bilayer, you're not. Yeah?
The sample really looks like this? No. I mean, one edge is much longer than the other one.
Yes.
So, yeah. Okay.
I could show you a gallery of pictures of devices, but they're all more or less, we pick a pair of contacts that are close to each other, and so we know the conduction is dominated by what's between those two contacts. But I could also explain, I can show you many more multi-terminal devices. I'm trying to keep the story simple.
Just the question is, what's the maximum length that you see a plateau? So you say
I'm going to show you much more detail.
Okay.
Right, so just we'll be better to discuss it later. Here's an example of how here's the experiment that we did that established, for our, at least in our opinion, that this was really edge conduction. We made a contact geometry like this. There's a picture of the actual device. We call this a pincer geometry. Right? We have these two pincer-shaped contacts and then one little contact in between them. They all overlap the edge. And we do two measurements and compare them. Either we float that central contact and apply a bias between the pincer contacts and measure the current. And that gives us this black trace here as a function of gate voltage with this plateau in the middle. Or we ground that central contact and measure only the current that flows through between the two pincers, having eliminated any current that flowed near the edge of the sample. And you see that when you do that, you get this blue trace, and this plateau is gone. But there's still conduction. There's still bulk conduction. This rise of the conductivity at high and low doping still occurs. So the bulk conduction is switching on in that region there as you go to high N or P doping. But the edge state, we've shorted it out. And we use this basic idea in many different geometries, for separating the edge conduction and the bulk conduction by basically shorting contacts along the edge to prevent the current flowing along the edge. So when I'll show you measurements on the bulk later, that's the essence of how we extract the bulk conductance. We just short out the edge conductance. Here's more indirect evidence, but yet in a more standard procedure that we're looking at edge conduction. This is a non-local measurement. We apply a voltage between those two contacts and measure the voltage between two others that are far out of the normal current path. And we see that in a range of low densities, the voltage that appears off here can be almost unity times the voltage you apply. So it's as if these two contacts are connected to these two by wires that go along the edge. Okay, and we see that plateau there is where these edges are conducting and dominating, and the edges and the bulk is insulating. As you warm up, it decays because you get more and more current flowing through the bulk. But an interesting thing to note is that there's still some of this non-local signal, this enhancement, even at room temperature. So this is somewhat indirect evidence that those edge channels are really, really strong, and they're still there and still conducting. They're contributing something to the conductance of the sample, even at room temperature. Another way that we know this is edge conduction is by applying a magnetic field. These are measurements at 10 Kelvin, so quite a high temperature. And we have this plateau here in the black trace, which is without a magnetic field. When we apply a magnetic field, it basically removes this plateau, okay? And it's switching off the edge conduction. it doesn't affect the bulk conduction. So what you see is the conduction, this blue trace is just the same as the black trace, but displaced downwards because you switched off the edge conduction. And the difference between them is this red trace here. It's very uniform, you see. So we know that at least in this range in the middle here, this conduction, this red trace corresponds to edge conduction. So it seems a reasonable hypothesis that this is edge conduction that is continuing to occur even once the bulk is turned on. Okay. Oh, whoops, there's another figure. Now, if you're not yet convinced it's edge conduction, hopefully this will convince you. We collaborate with Yongtao Cui at UC Riverside. He started the measurements at Stanford where they developed this technique, and he's now set it up himself at Riverside. He uses scanning microwave microscopy, or MIM, microwave impedance microscopy, where you basically have this metal tip you position above the sample and you measure the reflection of radio waves or microwaves from that tip. And it tells you about the impedance of the sample right underneath it. And these are basically images, raster scans of the impedance of the sample as a function of position. This is an optical image of a large WTe2 flake. And these are MIM images of little edges of that samples, the edge of that sample. You see, and you see, and the bright signal here, which is the imaginary part of the MIM, the outer phase part of the MIM reflected signal, which roughly measures the conductivity. So it's very bright all around the edges of this sample. And it reveals a few things that you wouldn't know just from looking at the optical image. Right? You see these zigs and zags here. That bright conducting region just follows the edge very nicely. But you see here in the optical image what looks like a nice straight edge. Whoops. But you look close in, you look with the MIM, and you see there's something else going on here. You see there's all these little insertions, these lines in the edge. And what these are, we're pretty sure, is small tears and cracks in the edge. See? And when your edge, say, gets to a crack, it basically goes around it. Right? There's two edges there, and it goes into the sample and then back out. So your electrons actually have a long way to go to get along this edge, right? And sometimes they have a nice, easy journey along a straight edge, but sometimes they have a microscopically nasty path to get along the edge.
Was that image done through boron nitride?
This is measured under thin capping boron nitride, typically 10 nanometers. It works. It limits the resolution if you make the boron nitride thicker. Oh, that's a 2-micron scale bar there. This is about 80 microns across. That's the biggest, by far the biggest piece of WTe2 we ever found, actually. And Yongtao went and destroyed it by scanning a focused X-ray over it to see if he could pattern it, but fortunately it was after he'd taken these nice images. Yeah?
Is that like a uniform thickness?
This?
Like are those 3 regions all monolayer?
This is all a monolayer, yes. And if it was ever a bilayer, we wouldn't see the edge glowing like this.
So why is the optical contrast going to change across the thing?
Oh, it's just a microscopy. It's just the illumination varies across the sample. We don't have a very good microscope. Okay. This is an image of an edge of WTe2, a MIM image, between 2 graphene contacts. We can measure its conductance at the same time, but I won't dwell on that. What I wanted, the only thing I want to point out is if you take a line trace, that's a trace in position along there, and then you vary the gate voltage, you get something like this. So we're sweeping in position as we change the gate voltage. Positive gate voltage, you see that the bulk turns on, N-type conduction. At negative gate voltage, you see that the bulk turns on again. In fact, we didn't go to high enough gate voltage in this sample to see it very clearly. But you see there's a range of gate voltages where the bulk is insulating, and yet the edge is always conducting right across this gap. It's always there. There's no gap in the edge. It's a gapless mode at 0 magnetic field, as you expect, for a quantum spin Hall. I'm going to skip. Yeah, that's good. Here's just an example of the kind of thing you can learn with MIM, is that you can see where the edges exist and where they don't, where you can't tell by DC transport. You'd never know by any other means than the MIM that I know of where that conduction is actually happening. This is a piece of WTe2 that's only partially covered by boron nitride. So this region of it has been oxidized away. And what you see is that the edge that's been removed by created by oxidation conducts just the same as the other edges of the exfoliated flake. So it means you can create these conducting edges by patterning this material. In principle, you could make these helical edges go where you want to. Right? What you also see is there's these internal lines. Those we're pretty sure are cracks. They're not grain boundaries. We know because we can do Raman and see that the crystal orientation is the same in every region of the crystal. So we're pretty sure they're cracks. But we can't see these cracks in any other way. We don't know that they're optically or in AFM. We only see them because they produce these conducting lines inside the sample.
They should have double the conductance, right?
Or more, yes.
Well, the cracks.
If you put a contact there and a contact there, then
Just in the microwave impedance microscopy.
oh yes, right.
They should be double.
So you see they're brighter,
But are they double?
and it takes some modeling to relate the MIM signal to the conductance. Okay, and we are not sure whether that's the case, that they're double or not. We're not sure how to model these actually.
But in relation to the edge, there should be a single relationship.
Yeah, you'd expect that to, like, if you could measure the conductance of that, you'd expect it to be 2e squared over h, and this would be 1, right? But since these are kind of quasi-ballistic, extended one-dimensional objects, it's not entirely clear, at least to me, what you're really measuring when you do the MIM signal and how you should model that. So if people have thoughts about this, you know,
My thought is just,
yeah.
without knowing how to model it, just the ratio of the MIM signal there to the edge.
the MIM signal is not proportional to the conductance, unfortunately. Okay, it's very nonlinear in the conductance, and it's somewhat non-local. See, but you can see that and we always see the internal edges are brighter. The cracks are brighter, I should say. Right? Yeah.
Would a dislocation in the plane also give rise to, if it's not a crack or a separation, would a dislocation give this effect or not necessarily? Because then they
Well,
would
a
still have the same-
dislocation in 3D is a line, and in 2D it's just a point, right?
Yeah, okay. So
You don't. This has to be a grain boundary or a twinning boundary or something. So you also, there's some dirty laundry that we have to be honest about here. We found by using the MIM that a lot of other stuff can happen as well. And now we know what goes wrong if we don't have a perfect sample, and we wouldn't be able to explain this stuff otherwise. We know that sometimes contamination gets in, and we see in the topography map that there are these blisters where material is trapped between, say, the WTe2 and the boron nitride. And what you see in the corresponding MIM image is these little circles around these blisters. And what we think is that under the blisters, the material is getting partially oxidized. So you're switching off its insulating properties, or you're turning it into a normal insulator, and therefore you get a boundary mode basically around that oxidized region. You've got a hole inside a topological insulator, and there's a boundary mode around that hole. Okay? You see these little donuts everywhere. You also see lots of cracks. Cracks are common. It depends how you prepare your material, what pattern of cracks you get. But another thing you see is you can understand why sometimes you make a device and the damn thing doesn't conduct. Even though it looks beautiful topographically and optically, it doesn't conduct. We know that in this device, the reason was that there are insulating regions right around, wrapping around the edges of the contact. And what we think happened, but you see on the edge of that insulating region, there's an edge. There's a nice conducting edge there. It just doesn't touch the contact. It couldn't get through that insulating region. Okay? The insulating region, we think this happens because of tenting. Because when you put the WTe2 down over the edge of the platinum contact, there's a channel right? It wraps down like that. It goes down trying to conform, but it doesn't manage. And there's a little channel there, and air or water or something can get in there and cause the material whoops. I wish this worked. I just paid $40 for this. You see, there's this, right, you get this oxidized channel around the contact and the things. It looks, you thought you made a nice device, but it insulates. And here's a diagram indicating all those things that we've learned, the problems that can happen that you can see in the MIM, basically. And this makes this, it causes reasons for pause when you're interpreting the DC transport measurements. If you don't know what your device really looks like, if you're looking, say, for quantized conduction, right, and you don't, without being very careful, you don't know whether you've got additional channels inside that are conducting, or whether your edge has got lots of tears in it, or whether it's partially oxidized and you've got some bulk conduction going on there as well. This MIM allows you to really be much more sure what you're measuring. Yeah, there was a question. Two questions. Three.
Magnetic field in MIM measurement?
Yeah.
So what
I
happens
skipped the
when you-
MIM measurements. I skipped the field measurements, but the conductance is suppressed somewhat. We can only do it at 4 Kelvin, so we don't expect a huge suppression of the edge of the magnetic field. We can only go to like 4 Tesla at 4 Kelvin, but we see some suppression of the edges, and the bulk is completely unaffected by magnetic field. Yeah.
No, it's nice too how you make the contacts this way, that you can see, you know, like there's some crack forming between the contact and your blade.
Yeah.
But what prevents you guys from doing it etching and then put the contacts like so some sort of
Fab.
etch contact?
Okay, there's a lot to be said about how to fab these devices, but the main limitation is you have to prepare it. The WTe2 can never see air. Okay, so you've got to think of a way of making contacts that doesn't involve exposing it to air in any way. And the only way you can do that is to prefab the contacts. It's the only way we can do it. If you had some fancy fabrication system set up in a glove box, you might be able to do it. But it's very hard. So basically, you pre-make the contacts. I want to get onto the other phases of WTe2, so I will just very quickly skip. I'll just say that there's a lot of mesoscopic phenomena that we see in the edge conduction, and it's also seen by our fierce competitors over at MIT. Sam Fung, this is from his paper this month. This is from our paper last year. This is the effect of this is mesoscopic fluctuations. This is the effect of magnetic field. It's complicated. It's not what you would hope, just a simple opening of a gap at the Dirac point in the edge. However, there is a very large magnetic field effect on the edge conductance. It's suppressed dramatically, and at 1 Kelvin it can be suppressed by orders of magnitude by a few Tesla, which is important evidence that it's really a helical edge, right? You expect helical edges to be very susceptible to destruction by mixing the forward and backward propagating modes and have opposite spin. If you put a field on with the right orientation, it breaks time reversal and it ruins the helical edge. So you see huge effects of magnetic fields. This is analysis of the effects of the magnetic field on the mesoscopics and the edge conduction, which I could talk to you about if you're interested. This is statistics of our devices and Sam Fung's devices as a function of spacing of the contacts, just showing that there's this tendency. So if we had ideal contacts for a single edge, we'd expect the conductance to get up here, the top of the graph, E squared over h. It only gets up to about half of that in our shortest contacts, shortest pairs, which are about 100 nanometers across. Sam Fung's go down to about 50 nanometers. And here his devices are coming down to, there's a cluster of them that are relatively close to the expected quantized value. So it's looking kind of quadrant spin Hall-y, but it's not perfect by any means. And the reason why that is just too complicated to discuss. And there don't seem to be any theorists who are even able to explain it. The second phase of this material is that it superconducts without doing anything else than turning up the gate voltage to the highest value you can get to and cooling the device. You see that the conductance at high positive gate voltages suddenly drops off dramatically by orders of magnitude. So at low gate voltages, it's relatively temperature independent. This is four-terminal resistance versus density. At zero density, it's an insulator. Okay, for hole doping or p doping, it's somewhat quasi-metallic. For n doping, it becomes kind of quasi-metallic. But above 5 times 10 to the 12 per centimeter squared, there's a phase transition, and it becomes, or it's something like a phase transition, critical point maybe. And above that, the conductance drops off. So at high densities, it becomes, resistance becomes unmeasurably small. This is just looking at the same thing from a different point of view. This is how the resistance drops off as you cool, and it varies, and it's density dependent. So just below 5 × 10⁻², it's basically metallic. It's almost completely independent of temperature. Okay, as you rise to 20 × 10⁻² centimeters squared, you get a good drop off of 3 or 4 orders of magnitude in the resistance as you cool below about 800 millikelvin. And by analyzing this, we can kind of construct a phase-ish diagram. This is temperature, this is density. Okay, there's a transition as a function of density in this range of around 5 × 10⁻². But of course, it's blurred, right? This is a very, very thin film with a low conductivity, so you don't expect under any circumstances to have a sharp superconducting transition. You have a broad one. But if you look at how the position of this transition depends on density, it's kind of like this, like it's at the edge of a dome. And we can apply a perpendicular or a magnetic field and see that it behaves in pretty much just the expected ways for superconductivity. It's very sensitive to a perpendicular magnetic field, so if you apply just a few tens of millitesla, you can basically turn off the superconductivity. The in-plane magnetic field is much, much less sensitive, so you need to apply several Tesla to remove the superconductivity in plane. And a simple analysis at a Tinkham level yields an estimate of the coherence length of about 100 nanometers. Mean free path of the electrons, we reckon, is around 20 nanometers. And we reckon that the effect of the in-plane field is due to pair breaking by a spin-orbit scattering. And if we do that, we get, according to that theory, we get about 2 picoseconds spin-orbit scattering time. Yeah?
So the step there is the step of spin Hall effect, and then it drops to 0? What's
no,
this?
Good. I should have mentioned. So here, there's no the edge conduction is negligible. So at these temperatures, our edges have frozen out. So it's something we don't understand, which I skipped over, which is that the edge conduction in WTe2 in both our devices and I think in the MIT devices, eventually at low enough temperature, it freezes out. It becomes gapped. So below 1 Kelvin in this device, there's no edge conduction left. So all we're doing is measuring the bulk conductivity here. Okay? Good.
So if you would want to do a Josephson junction there, you would need to change temperature between region.
Yes, in this device. But we do have it doesn't always freeze out. And so I've got another device I'm just about to show you where there is edge conduction and superconductivity at the same time. So it's not hopeless. But that's a good point, yeah. Okay. I'll skip that. And this is an attempted scaling analysis, but I don't think it makes much sense, so I'll skip that. Okay, unless anyone wants to come back, ask questions about it. Okay. So this is basically the phase diagram that in terms of the relationship between the superconducting region at high positive densities and the insulating region. We think it's a topological insulator. It has edge conduction up here around 1 Kelvin and above. Down here, it's the edges are kind of frozen out. And that's our best estimate of this phase boundary. And I want to emphasize that this transition from insulator to superconductor happens at a 5 times 10 to the 12 centimeters squared, which is only about 0.5% doping, which my understanding is much, much smaller than the doping that you normally need in a material to get superconductivity, like in a cuprates or in a molybdenum sulfide, for example. You can dope them ionically. You get up to about 10% doping, and then you have superconductivity. Here, you just tickle it with a few extra electrons, and it becomes superconductor. It switches from an insulator to a superconductor. What kind of insulator is that? Okay, this is not an answer to that question. This is finishing off the last thing, and in response to a question that was asked just now. We have a sample here that, where you can see the conduction in the edges at the same time as the superconductivity, and here's the evidence that they're both present at the same time, but I will leave it to questions to discuss that because it's a bit complicated. But I'm going to assert, for the moment, I'll just assert that we have evidence that the edge states remain in the presence of the superconductivity sometimes. So I want to talk, so phase 3 of WTe2 is the answer to the question that I just posed. What is the nature of this insulating state at low densities? And it has some pretty strange properties, in my opinion. In my experience of measuring semiconducting devices and metallic devices, I don't know what to make of this. This is why we're measuring a semimetal, because we expect some strange, interesting things to happen. It has a two-dimensional semimetal. What should it do? Graphene is well known, but what about others? Okay. So these are measurements of the bulk conduction in a monolayer, the one on the left here. So the way we get at the bulk is we ground the edges. Okay, we just connect. So we apply a bias at the top there, and measure the current out at the bottom there, and we stop the edges from carrying any current by grounding them. If someone's got a better idea for how to do this, please let me know. But separating edges and bulk is a tricky business. Anyway, this is what we do at the moment. So we call this the bulk conduction. I just call it the conductance. Okay. And as a function of gate voltage, of density, of doping, basically, and we see that at a room temperature, it's weak. As you cool, it develops this V shape. And at a critical temperature, I call it a critical temperature, Tx, of close to 100 Kelvin, that becomes a pretty sharp V that just, the bottom of the V is getting close to insulating, and it's right at zero doping. It's right at the uncompensated point in this material. Okay. As you cool further, it becomes gapped. We can actually measure activation in this region below this critical temperature, 100 Kelvin, and we find that the gap peaks, that's the activation energy down here, we find it peaks at about 50 millivolts right at that point there, which is not that far off KT, where this is, well, it's actually, yeah, it's larger than this. I'll skip over this. This is just looking at the same measurements from a different point of view. But this is strange behavior. You might think I can understand this some way with some combination of maybe bands that are uncrossing and some strange dependence on the mobility on density. I can get this V shape. Well, if you think you can do it, please give it a go, because I tried and I can't. I can't reproduce anything like this. Moreover, we see something very similar in bilayers, which is surprising because they ought to have pretty different band structure. According to any band structure calculations, they're still semimetals with small pockets of, the bilayer is still a semimetal with small electron hole pockets, but it's very different Fermi surface. Yet we see basically essentially the same thing that happens. As you cool, this very sharp V shape appears centered on the point, the neutrality point, n equals p, or when there's no net doping, okay? And at a certain critical temperature, which in the bilayer is 20 Kelvin, the bottom of the V goes to 0 conductance, and below that it's activated. So we have this similar behavior, but with a lower critical temperature, 5 times lower in the bilayer. Okay. What is going on here? I've no idea. But ideas that come up are, we've got small pockets of electrons and holes. Surely there are strong Coulomb interactions between these. There's going to be some kind of correlations of the electron and holes. And a model for that, an old model for that, but Halperin was one of the people who introduced, is the idea of an excitonic insulator. You go into a condensate of excitons built out of these, of an electron from the electron pockets and a hole from the hole pockets. Right? But that doesn't go very far as I can tell, to explaining any of this behavior that I was showing you. It just indicates, the idea indicates that something special might happen when you've got exactly the same number of electrons and holes. So all of your carriers become excitons and they all condense out, and then some phase transition happens. To look at that from another point of view, we did some experiments to look for a gap opening, and to cut out the details of how we did it, which I can tell you about if you're interested. Essentially, we use graphene to measure the compressibility of the material as we dope it. And we can extract the chemical potential in the material in a WTe2, that's this vertical axis in millivolts, as a function of the density of the doping. There's neutral doping in the middle. And what we see is that around room temperature, basically there's no feature at all. It's like there's a smooth density of states. And as you cool, you start to develop a soft anomaly in the density of states, or we shouldn't really talk about density of states if this is a correlated material, but in the compressibility, if you like. The compressibility is starting to become small here. And below remember I said the critical temperature in a monolayer is 100 Kelvin. Below 100 Kelvin, this anomaly becomes a step. Okay? It becomes a very narrow, sharp feature. The chemical potential jumps. And it jumps exactly at this neutrality point where the conductance has this sharp V. Another interesting thing is that we see that below lower densities, this becomes flat here. The chemical potential becomes independent of density. That means the compressibility diverges. You can keep adding electrons to the WTe2 when you're in this regime, and the chemical potential doesn't go up. And then when you get to this point, it suddenly jumps up. Okay. Something similar but weaker feature happens at lower temperatures as expected in the bilayer. The temperatures went for a walk there. And here, just summarizing that, is this we see at the same time as we see a very, very sharp minimum in the log of the conductance, that's a log scale, the blue line here, we see this step in the chemical potential. This is at 50 Kelvin. It just gets sharper and sharper as we cool it down. But the temperature at which this sharp feature appears, and that step appears, is 100 Kelvin in a monolayer. What is going on there, I don't know if there's any theory for it. That's one reason I asked Philip, I forced Philip to invite me to come to Harvard so I could ask all the brilliant theorists here what the hell's going on.
What if that we just can bind onto with simply single particle pictures, and then in principle that you can extract it, then what is the density of state to look like with given chemical potential? Then
you can't do it. You cannot do it. You simply cannot find a density of states that is consistent with these measurements.
And you can construct the experimentally measured density of state from there.
I can take this and invert it and differentiate it to get a different density of states. But if I do that at each different temperature, I get something completely different. Okay, it gives me something that I can just put all, I can map all.
At the low temperature, and then kind of build up, and then you can just kind of throw the temperature broadly.
Well, okay, this at low temperatures diverges. Okay, this becomes flat. So the density of states diverges there. What am I supposed to do? Okay, so you get, if you ask what is the density of states here at the lowest temperature, basically it's infinite, and then There's a finite region, then it's 0, and then it goes down to a steady thing. Okay? But you can't take something that's infinite and then does that, and then say have it evolve into this. I mean, you can just mathematically manipulate this and turn it into a density of states, but it doesn't seem to make any sense to me. See what I'm saying? But maybe I'm missing a simple explanation. I've been trying and failing, but I'm glad. Yeah, you're asking exactly the same questions that we try and do this, and yeah.
So the whole side definitely seems strange. But on the electron side, can you just cite what that slope would mean for an effective mass?
Yes, you can only very roughly estimate it, but it's roughly the free electron mass, which is rough. The band is consistent. The conduction band is not that, the effective mass, if you take the DFT calculation, is not that far off a free electron. Good. Finally, the last and the newest and freshest phase comes when you're all too exhausted to digest any more, right? I apologize, but I'm going to tell you very briefly. This material, WTe2, is also polar. In a monolayer, it's not. It's a centrosymmetric. There's a center of symmetry, seen from two different directions. But once you stack it, the space group associated has a polar axis. That means if it was an insulator, it would be a pyroelectric. It would have a built-in polarization. But it's not. It's a metal. It has a polar space group, but it's a metal, so it can't have any internal electric fields. Okay. Polar metals are supposed to be very rare. In fact, there was a Nature paper 2 years ago on osmium oxide claiming this is the first ever polar metal. But that's just not true as far as I can tell. WTe2, it's a polar metal. It has a polar space group if you just look it up. This became obvious to us in our measurements when we were studying these things, and we were putting opposite signs of voltages on the two gates. What we found is so you apply this perpendicular field, E perpendicular, which is basically, if you put opposite voltages on the two gates, what we find is you sweep that perpendicular field up and down. For a trilayer, you see is massive hysteresis. For a bilayer, also big hysteresis. Monolayer, no hysteresis at all. Exactly what you expect, because the monolayer is centrosymmetric, it's not polar. The bulk, and presumably down to bilayer, it's polar. It has this polar vector out of the plane, and clearly what's happening here is you're reversing that polar vector. By sweeping this external field, you're flipping the polarization state. Okay? And it shows up in the conductance. The conductance of this stuff depends on its polarization. Which is, so this stuff is behaving as a ferroelectric. And it's the first ever conducting or metallic ferroelectric. Okay? Ferroelectrics are always insulators or maybe semiconductors because those free electrons screen the polarization. The reason it's ferroelectric, we can call it ferroelectric, is because we can switch the polarization. And the reason we can switch it is because it's so thin. The electric field penetrates it, which doesn't happen with a bulk metal. We can detect, yes?
Why does the conductivity depend on the polarization?
Good question. It does. If we understood why the conductivity, if we understood the basic mechanisms of the conductivity in this material, it would be nice, but we don't. So we don't know why it depends on anything, actually. Right? As I've been saying, it's very strange. But it does depend on everything. I could say, I do know a bit more than that, but I do not know the mechanism. Okay. Now, I could convince you, I think, that it was a ferroelectric by telling you about these measurements, which I don't have time to. But we use graphene as an electric field detector. We can detect basically the polarization, the transverse polarization of this layer, and we can see the two polarization states in this range where it's bistable. We can see the flipping of the polarization here. So we can actually measure the polarization, the spontaneous polarization of that layer. Okay, and this is basically what happens. You have this graphene layer here, and Here's the bilayer underneath it. There's the gate down there. When the polarization of this bilayer reverses, charge shifts around, and that changes the electric field, which affects the conductance of the graphene. And we can quantify the polarization roughly based on that. And it turns out that it's equivalent to shunting a density of about 10 to the 12 electrons per centimeter squared from one of the monolayers to the other in this bilayer. That's how it depends on temperature. So it's a robust effect. It is there up to room temperature. And it seems to be heading for some kind of phase transition to a paraelectric or nonpolar state somewhere around 400 degrees Kelvin. This ferroelectric switching effect, it depends somewhat on the density of electrons, which is in these graphs here if you're interested later. That's something interesting because it's a metal. Being a metal, you can do transport for it, you can change the density of electrons, you can modify the ferroelectric switching properties. You can't do those in a conventional ferroelectric. So, and analysis, yeah.
The reason why conductivity changes with ferroelectricity, is it related to the fact that you actually have a small number of charge carriers and contact might change as well?
It could involve the contacts. I mean, we think that these are 4-terminal measurements, by the way. So to some extent, these don't involve the contacts, and this behavior is very robust between different sets of contacts and so on.
If you actually believe that it's truly ferroelectric, that means that you will actually develop different charge sheets as you actually flip the polarization. Right?
Yeah.
And then you're actually moving the charges around in a monolayer, bilayer, or bilayer, or trilayer.
Yeah.
That means the charge density should change.
Yeah.
Which may or may not affect it.
It might. There's an asymmetry between the effects of the two gates, which might be because they affect the contacts differently. So, yeah. So here's my summary. These are the 4 faces of WTe2, thin WTe2 that I told you about. Quantum spin Hall behavior, strange behavior of the insulating state in the bulk. You can gate it to a superconductor, and it's ferroelectric. So a fairly modest list of results for first measurements on the first ever two-dimensional semimetal. I hope you agree with me that it's pretty exciting. I just can't wait to see what happens in other two-dimensional semimetals. How much of this is generic? How much more phenomena there are to discover in these types of materials. So here's a to-do list. It's just part of our to-do list, and you can read those for yourself. They're all kind of obvious. One I really want to emphasize, though, is the hardest of all probably is to, if you want to do anything with these wonderful quantum spin Hall edges, you're going to have to figure out a brute force way of making better edges. And otherwise, you're just fantasizing about braiding your Majoranas. And the key players involved, their pictures are down here. I already mentioned them, and these are our funding sources. Thanks for listening.
Share with us. I think we asked for a lot of questions, but I'm sure that there will be probably more questions here and there. Yeah?
Have you measured the Hall effect as a function of the voltage and temperature in the bilayer?
Yes, we have. The Hall effect in the bilayer is interesting and complicated. In fact, we've also seen quantum oscillations in the bilayer. I'm on record, so this is very new, but essentially we see a Fermi surface forming in the bilayer under some circumstances, and we have Hall measurements that are somewhat consistent with that Fermi surface, but the actual details are complicated, and we're still trying to work them out. But more or less, to some extent, they're consistent with our expectation that it's a semimetal with overlapping bands, and that at extremes we can get just electrons or just holes, and in between we have a mixture of electrons and holes. which of course gives you a junk Hall signal. So the Hall signal only makes sense when it's highly doped.
If you apply magnetic field in plane, is it supposed to gap like the edges on the right and the left and not gap the edges? It's more, I don't know, theoretical actually, I don't know the answer.
Right, well the answer to questions about how the orientation of the magnetic field matters is confusing. Okay, the orientation of the spins in these edge states is not known. It's not perpendicular to the plane, that's for sure, and it probably depends on the orientation of the edge, and it may depend on K as well. So
maybe in plane we light some of the edges and some
yes, it could be, and we haven't actually been able, we don't have the facilities to rotate the field in plane to see if there's an effect, but I'd love to do that, yeah.
Other questions? All right.
If it's indeed a polar metal, you can maybe do like some sort of electrical tip contact to write a pattern, create domain, and then you track and then image that.
Yeah.
And see whether it's indeed polar.
I think we ought to be able to create domains with gates, with an FM tip, or whatever. And yeah, someone earlier suggested this be very. You could create domain walls between the two polarization domains, and maybe study their properties. But it's interesting that all these things are happening in the same material, right? So the interplay between all these things and the gate tunability of everything, the switchability of from insulator to the superconductor and the ferroelectric, they're all it's all just gate voltages. So by patterning gates, you can play a lot of games with these things.
How do you perform the measurement of compressibility? How does it actually set up?
Do we have time for me to? So this is the setup we use. Oh, not here. That's how we measure the polarization. Where was it? Oh, it was way back. Yes. You all remember better than I do. That's how late it is in the day. Are you all going to copy me? Okay. I don't mind you copying me, but I want a trademark. I'm being recorded, right? I'm trademarked.
Using the graphene that was in minor to
Yeah.
That was probably trademarked by them here.
Sure, this is just a very simple, obvious thing to do if you're in the business. You use graphene as an electric field sensor. And we basically measure the conductance. We have at the top gate becomes graphene, and we can measure its conductance. And what we do is so that we apply a voltage to the bottom gate, and we tune the voltage applied to the WTe2 such that the graphene's at its Dirac point. Make sense, right? And if you do that, you know the graphene is undoped, and you know there's no electric field going into the graphene. So you know all the electric field from the back gate all the flux is going into WTe2. So you know the density. So that gives you the thermodynamic doping level in the WTe2, right? And this voltage here directly connects the chemical potential in WTe2. So you directly measure chemical potential versus, and it's just it's very simple, and we weren't the first to do the basic thing, but I think we got it to work very nicely in these devices. We use basically the same setup to measure the polarization of the bilayer, which affects the graphene above here as well. So I think it's, I'm not sure, this hasn't been, this technique can be used for other materials, right? And it's a beautiful thermodynamic technique. It's static. It's quasi-static. Well, you don't need to oscillate. You don't have a capacitance to measure. So even a poorly conducting thing, you can use this. So I think it's great.
One question for a superconducting transition that you showed. So the resistance doesn't drop that sharp. So
Right.
what is the length between the electrodes?
Micron, half a micron.
Right, because if those tiers or
Well, the current path is 5 to 10 microns, and then voltage probes are a micron apart. So there's no single length scale. What's the question? What's the question?
I was wondering if that drop is because of, I mean, you have these kind of you call it spheres or domains or whatever on the transcendental, right? So if they, I think you also mentioned like a science paper where they do length dependence, right? So you can shrink the electrode separation
Of the what? So length dependence of the superconducting transition?
Yes.
I don't know about that. No, there's no papers on this yet.
No,
right?
but
For the edge state?
For the edge state.
Okay. Right.
So where they see that for a smaller distance, they can get the conductance very close to half of h over d squared, right?
Yeah.
So I'm wondering if, I mean, you can also use the same for the superconducting measurement, where you don't see a sharp transition. That's why I asked you how far the electrodes are. You mentioned they are 1 micrometer apart, right?
Yeah, don't see a sharp transition as a function of temperature or as a function. I mean, that we can take probes, we can use voltage probes that are further apart and we get exactly the same thing.
Make them closer, right? So because of those.
Why, yeah, I don't really understand why that would.
There might be some weak links, right? Since the sample is not that uniform or.
Right, there might be, yeah. So there's a lot of things to do that we haven't done. Yeah, looking for weak links, inhomogeneities, maybe anisotropy. Yeah, good. No, sorry, we just haven't done it.
Okay, with Denmark, let's thank the speaker once more. From Professor Westberg, anyone that's thinking that yes, 294 come down and sign off.
This kind of
Well, exactly. Well, I know all about his experiments because I followed them. But just doing it. But he didn't have graphene. Yeah. Well, I'm not saying it's new to medical. But what you have with graphene is you know the absolute charge, right? So you can measure. Yeah, of course. There's many previous measures of compressors. I think what you're saying is I need to be more careful. Well, I will. Well, I think I wouldn't be the first person to patent something that had already been done 25 times.